Hello there. In this video, we're going to discuss an extension of the distribution property known as the binomial theorem. In particular, we're going to be focusing on expressions that look like x plus y to the power of n, where n is a natural number. So this is going to be pretty much a quick way to expand binomials of this form. Alright, so to begin, we're just going to state just a couple assumptions on x, y, and n so that there's no confusion about a couple things. First off, we're going to assume that x and y are either 1 or both are not equal to 0. If 1 is equal to 0, then it's pretty much a trivial expression, and if both are 0, then it's pretty much a useless exercise. Also, we're going to assume that this number n is going to be in the set of natural numbers, either 1, 2, 3, 4, 5, 6, or 0 is perfectly fine as well. So let's just work through a couple of these to sort of see if we can capture a pattern. Alright, so let's first look at the case when n is equal to 0. So that's going to give us x plus y to the power of 0. And since we're assuming that x and y are not equal to 0, the sum is greater than or equal to 0, and any non-zero number raised to the 0 power is going to be equal to 1. So that's not really an exciting thing, but this is our result for that particular case. Now let's consider the case when n is equal to 1. So that's going to give us x plus y to the power of 1. So pretty much what this means is we're going to multiply x plus 1 by itself pretty much none times, namely we're only going to have one of these x plus y's, so this of course is just going to be the same as x plus y. Pretty much anything to the first power is just itself, so this is the expression that we have. So one of the things that I'm going to do here is I'm going to emphasize that there are coefficients in front of x and y, namely 1. This is going to be extremely important very soon. So the next thing I'm going to look at is n is equal to 2. So as we know, this is going to be the first slightly interesting one. So we know this is the same as writing x plus y multiplied by x plus y. So as usual, we know we can distribute this out. And once we distribute and combine like terms, we're going to get x squared plus 2xy plus y squared, where the numbers in front of x squared and y squared are, of course, equal to 1. So that gives us that. Now let's just do one more for fun. Let's do n is equal to 3. So this is going to be x plus y raised to the third power, which of course is the same as x plus y to the second power times x plus y. So we know x plus y squared already. That's just x squared plus 2xy plus y squared, and we can multiply that by x plus y. So let's distribute x squared into this term. So this is going to give us x cubed plus x squared y. And then we can distribute the 2xy term. So that's going to give us plus 2x squared y plus 2xy squared. And lastly, we're going to distribute our y squared into the last term. And that's going to give us plus xy squared plus y to the power of 3. Then I'm going to combine like terms. So notice x cubed and y cubed are the only cubic terms in this. We have an x squared y and 2x squared y, so you can combine those two terms. You also have a 2xy squared and an xy squared, so we can combine them into 1. So we're just going to have 1x cubed plus 3x squared y plus 3xy squared plus y cubed. So notice this is our expression for x plus y to the power of 3. Now, notice we have coefficients 1, 3, 3, and 1. And we can continue to do this for the power of 4. So I leave as an exercise for the next one. I don't know if this is example 4 or not, but anyway. What about n is equal to 4? So what do you think x plus y to the power of 4 is going to expand into? So if you expand this, you'll find out this is going to be 1x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the power of 4. So have I memorized what this expands to, or is there actually a pattern to it? So the first thing to notice is we can rewrite this as 1x to the fourth y to the 0 plus 4x cubed y to the first plus 6x squared y squared plus 4x to the first y cubed plus 1x to the 0th y to the fourth. So if you look at the powers of x, we have x goes from 4 to 3 to 2 to 1 to 0. So we're decreasing from 4, which remember is the power of our binomial, and it decreases from 4 all the way down to 0. And the other direction we have 4 goes to 3, goes to 2, goes to 1, goes to 0. So it increases from left to right from 0 all the way up to 4. So the powers on x and y are obvious what's going on there. The only thing that remains is, okay, what about these coefficients in front of each of these terms? Well, you should recognize these terms as binomial coefficients. So 1 is the same as 4, 0, or pretty much any natural number choose 0. This number is 4 choose 1. This is 4 choose 2. This is 4 choose 3. And this is 4 choose 4. And if you do not believe this or you're not familiar with binomial coefficients, you can definitely check out that video to sort of explore what binomial coefficients is. So of course, this number here is n, which in this case is 4. And this number here, 0, 1, 2, 3, 4, increases with the same value as y power does, right? So what we can do is we can sort of treat this as a term. So this can sort of be like k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, and k is equal to 4, and we can express this as a sum or express this in sigma notation. So we can rewrite this as the sum from k is equal to 0 to 4 of 4 choose k of x to the, okay, now how do we get to 4, 3, 2, 1, 0? So that can be 4 minus 0, 4 minus 1, 4 minus 2, 4 minus 3, or 4 minus 4. And in general term, that's going to be 4 minus k times y to the power of k. So this is the condensed representation of x plus y to the power of 4, right? And this, of course, can extend to what we refer to as the binomial theorem. So the binomial theorem generalizes this to any power natural n. So x plus y to the n is going to be the sum from k is equal to 0 to m of n choose k times x to the m minus k times y to the k. Right? This is a very beautiful and condensed representation. All right, so let's do a quick example of this. So let's assume we want to expand x plus y to the power of 5. So remember, a quick way to gather the binomial coefficients if this number is relatively small is we can use Pascal's triangle to sort of generate these coefficients, right? So remember that this corresponds to n is equal to 0, this is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, so we need one more row here to sort of get what we want. So 1, 5, 10, 10, 5, and 1. So this is going to be n is equal to 5. So these are the coefficients that we sort of want to use. All right. So this is going to be equal to, so we're going to start with the highest power of x. So that's going to be 5. Then we're going to have 5 times x, decrease x by 1, so 4, increase y by 1. Then 10x cubed y squared plus 10x squared y cubed plus 5xy to the fourth plus y to the fifth. So this is the expansion of x plus y to the fifth. Fairly easy, fairly quick, right? That's why the binomial theorem. And this definitely has a lot of applications in higher mathematics. So what if we want to expand something that is slightly different than this representation? Suppose we have x minus y to the power of n. So now we have a difference here. So no worries. So we can rewrite this instead as x plus minus y to the power of n. So what we're going to do is we're going to replace y with negative y in our binomial expansion. So this is going to be equal to the sum from k is equal to 0 to m of n choose k times x to the m minus k times minus y to the power of k. And what we can do is we can decompose this minus sign by using our properties of exponents. So we can rewrite this instead as the sum from k is equal to 0 to n of minus 1 to the k times our binomial coefficient x to the m minus k times y to the power of k. So this is our binomial expansion on a difference of terms. Alright, so let's just do an example of where it's just not x and y, where it pretty much is some other things going on. So let's look at the expansion 1 minus 2x to the power of 4, and let's expand this using the binomial theorem directly. So this is going to be equal to, so this is going to be 1 to the power of 4. So let's write our binomial coefficients also. So it's going to be 4 choose 0 times 1 to the 4th. And then we're going to have minus 2x to the power of 0. Then plus 1 times 1 to the 3rd, negative 2x to the power of 1. Plus 4 choose 2, 1 to the 2nd, negative 2x to the power of 2. And then we're going to have plus 4 choose 3, 1 to the 1st, negative 2x to the power of 3, plus 4 choose 4 times 1 to the 0 times negative 2x to the power of 4. Alright, so let's gather our binomial coefficients first. So this is row 0, 1, 2, 3, and 4. So we have 1, 2, 3, 4, 5 different terms. 1, 2, 3, 4, and 5 different terms here. So let's just replace those and simplify these powers out a little bit. So we have 1 to the power of 4, that's going to be 1. So this is going to be 1, that's 1, that's 1, that's 1, that's 1, so that's not really exciting. So we're going to have negative 2x to the power of 0. And then we're going to have plus 4 times negative 2x to the power of 1, plus 6 times negative 2x to the power of 2, plus 4 times negative 2x to the power of 3, plus negative 2x to the power of 4, right? So we know our powers of 2, so that's no big deal. So this is going to be equal to 1. So negative 2 to the power of 1 is going to be minus. So this is going to be 1 minus 8x. Negative 2 squared is going to be positive, so that's going to be 2 times 2 is 4. 4 times 6 is going to be 24x squared. 2 times 2 is 4 times 2 is 8, but that's going to be negative, so that's going to be negative 32x cubed. And then we have 2 to the power of 4, so 2 times 2 is 4, times 2 is 8, times 2 is 16x to the power of 4. And notice how these changes signs, so plus, minus, plus, minus, plus. You're always going to have that when you have something minus something to some integer power. So this is just an introduction to the binomial theorem in case you're already not familiar with it, which definitely has a variety of different applications in several fields of mathematics. Hope you enjoyed.